Hey there. In this video, I'm going to talk about some of the most foundational concepts in causal inference theory. These are called treatment effects. So, effect, let's actually break it down. So, effect is the impact of any intervention. So, intervention is a key concept in causal inference because causal inference theory deals with what needs to be done and not just analysis, because analysis is gives you probabilistic results, insights, but you actually need to act upon it. You need to implement certain things based on the insights. That's what causal inference really deals with. What causes something, and therefore, based on that, you need to take more of that action to bring about those desirable effects. So that can be increase in sales because of some campaign that you've launched, because of some discounts, promotions, any other kind of campaign strategy that you might have taken as part of your marketing initiatives. So the treatment is that intervention, the effect is the outcome that you want, that desirable outcome. That's pretty much in a nutshell what causal inference deals with. Of course, it's insanely oversimplified when I put it like that, but yeah, that's the field basically. But let's actually talk about now, specifically drill down into treatment effects. There are different ways to quantify the effect of an intervention, and these are there are several ways to do it. We're going to look at a few of them. So the first one is called average treatment effect. Let's actually look at the definitions and then we'll come to the equations, the mathematical formulation. Average treatment effect is simply the average treatment across the population. Okay, so this is undifferentiated. This is unadulterated in any other way. This is simply the average treatment effect. Okay, the average treatment effect on the treated. So first of all, when you're talking about things like causal inference models and causal methods, you obviously have control and test, right? So there are two parts to it. Of the population, you will be applying or implementing the method on a part of your population, of your observed population, and then there will be another part which will be the test. So it's the test that you will be applying it on, and the control will be the rest of the population, or a certain part of your population. So that's why there will be two different kinds of average treatment effect as well. So the average treatment effect, the first one is the overall one. The average treatment effect on the treated is specifically concerning those who receive the treatment in the study. The average treatment on the untreated, on the other hand, is the effect that's observed among those who did not receive the treatment. So that's the control. And then there's also another one which is called conditional average treatment effect. This is specifically for those parts of the population with certain values of certain variables. For instance, if there's gender as a variable, as a varying parameter among the population, then the average treatment effect among women, for instance, that gives you the CATE, or the conditional average treatment effect. So these are four of the important definitions. There are other definitions as well using treatment effects, around treatment effects, but let's focus on these few for now. So let's actually jump on to the mathematical definition now. So a unit's observable outcome is a function of its potential outcomes determined according to the switching equation. This is a switching equation, and as we'll see from it, very easily we can actually derive at this thing here, this little thing sitting at the bottom, which actually gives you the the causal effect essentially. So how can we use this switching equation? So essentially what it typically means is, depending on whether or not a treatment has been given to a particular unit, that actually gives you your outcome value here, which is yi. So your yi is defined by whether or not the treatment is given, which is given by the variable di. And now if di is 1, yi is actually given by simply yi1, as you can see, right? Yi superscript 1. And that's because di, when it is 1 here on the second part of this equation, it simply becomes 0. On the other hand, when di is 0, the first part becomes 0, and it's only the second part which remains, which is then the case where yi is simply equal to yi superscript 0. So the first one is the case where treatment is received, which is why it's di1. The second part is where treatment is not given, or which is where the outcome value corresponds to the outcome value where treatment has not been given. So if you just look at this paragraph here, that's what pretty much it talks about. So the rest of the stuff zeroes out. You can see why it's called a switching equation, right? So di basically acts as the switcher because it helps you switch between whether or not the treatment has been given or not. By the way, this is also part of what's called the potential outcomes framework, and that's developed by Julia Pearl, who is one of the most popular proponents in recent times of causal inference. There are others also who have built their approaches towards potential outcomes, rather causal inference, but potential outcome is this whole concept here, which is given by which also includes the concept of counterfactual, as we'll come to in a moment. But just to give you an idea of the theoretical background it's coming from. So now we'll go back to these theoretical definitions that we have sort of put forward or proposed, and we'll see the mathematical way they can be defined. So average treatment effect, remember, it's on the entire population. It's therefore the expectation of delta I. This delta I is given by the difference between the outcome of each unit when there is a treatment, and the outcome of each unit when there is no treatment. So that difference is simply the effect, right? So when there is a treatment, subtract it from it, the outcome of when there is a treatment, subtract it from the outcome when there is no treatment. That gives you that the delta basically gives you the effect of whatever you did, right, that treatment. So therefore the average treatment effect is the expectation of delta I. Okay, so that's the statistical definition of it. An expectation, which in this case is given, but the delta I is, in fact, we just replace delta I with its definition here, as we just talked about it. And then actually the third line here, this is derived from a property of expectation. We'll come to it in a moment, but for now just let's absorb it as and accept it that this is what is the outcome of it. So you just split it up into the two parts of it. Okay, so expectation of the outcome of each unit when there's a treatment minus expectation of each unit's outcome when there is no treatment. That's basically ATE. Now what's ATT? That is the average treatment on the treated. So that therefore this therefore becomes automatically, as you can see, there is this conditionality, right? The first one did not have any conditionality, the second one does have a conditionality, which is therefore expectation of delta I given di, capital Di, equal to 1. So this is the condition is that there is a treatment. So that's what it's only going to care about. It's not going to care about when there is so the overall condition is that there is a treatment, and then it becomes therefore E of, again, once again we replace the delta by this expression, or this part here, and then it's Di equal to 1. And then once more it follows that same property, because of which we split up these two. And then we have this case, the first part here, the expectation of yi1, when it's under treatment, given that it's actually got a treatment, and expectation of yi0, again, given that it's actually gotten a treatment. So the units that did not actually get a treatment, but so what would have been their situation if there were actually a treatment? Okay, so this is where so remember, if we go back to the definition, so this actually defines whether or not you actually got a treatment. Okay, so if you did not get a treatment, this is how the outcome looks like. But suppose if it were to be given a treatment, which is what is given by di equals to 1 here, so if you take that part here, this basically becomes a counterfactual, because this never really happened, right? This is a reality that was never even observed. The alternate reality was actually observed. So you can't have both the things. You can't have the cake and eat it at the same time. Essentially, that's the kind of thing. So it's basically what would have happened had treatment been given to those units which actually did not receive the treatment. We can't go back in time using a time machine, which doesn't exist in reality. But this counterfactual, if you subtract it from this value here, which is given by the effect which on the units which actually received the treatment and which actually did, given that they actually received the treatment, that is something that you have observed. So the difference of these two gives you ATT. The untreated is just the opposite, where you actually take the value this time. As you can see, in this case, the di becomes 0, because this is the case where the treatment has actually not been given. So this time, in this case, the second part of the equation is what has actually been observed in reality. The first part hasn't been observed, because you are finding out the expectation of the output, of the outcome of this treatment for the units which have, the units which have been treated, but given that they actually had not received a treatment. So this is a counterfactual. because this is again a hypothetical scenario that you are deducting it from. So that gives you your ATU. These are the most three important definitions. There was also the conditional average treatment effect. I've not given a separate mathematical formulation here, but as you can understand, this can be derived pretty much comfortably from the rest. Now let's actually look at some of the properties of expectation, because as you can see here, expectation here, this is a statistical formulation. uh, this is a statistical sort of notation that we have used. So expectation, linearity of expectation, so there are some properties that are important. Linearity of expectation simply means that you can split it up into these two things. So expectation of a of x plus by is a into, so the a comes before the expectation of ex, and then b comes before expectation of ey. You just sum them up. So this is called a linearity property, and this works whether or not they are independent. So the application here is that expectation of yi minus yi1 minus yi0, as we saw before in these cases, in each of these cases we actually saw that this sort of equivalence actually held. This explains why the ATE and the other two are written as the difference of the two expectations rather than the expectation of a difference, right? So these are the difference of two expectations rather than the expectation of a difference. That's the beauty of statistics. I mean, there's always a mouthful to describe complex mathematical forms. So whichever way is actually easier for you, the wording or the equation. So the conditional expectation is the second one, which is simply defined as expectation of x given a. That's your and if you're familiar with probability and if you have forgotten expectation, this might ring a bell, right? And this actually looks very much like conditional probability, and because it is, because it's very closely related, as we'll see in a moment. Average of x given event a. So this is basically like condition probability only, but we'll see the mathematical form of it. So in the formulas, expectation yi of 1 given di equals to 1 is the average potential outcome under treatment for the treated group. Like I was saying previously, the average potential outcome under control for the treated group. So this is basically for the treated group, the group that got treated, but under the condition that it's actually under control. So the potential outcome for when it is under control, this is the potential outcome when it's yi1. This is potential outcome under treatment for the treated group, because this is what has actually received treatment. In both of these cases, that's the case. So it's just giving an explanation of, as an so it's the conditional expectation which is basically given by these two. So that's why ATT is written like this. Okay, so that's where it's derived from, because it's just a linear application of conditional expectation. So it's given as expectation of yi1 minus yi0 given di equals to 1, which is equal to expectation of yi1 given di equals to 1 minus expectation of y0 given di equals to 1. You might have guessed this obviously comes from the previous thing that we just talked about, which is the linearity uh, principle, or the linearity linearity property of expectation. The third is the law of iterated expectations. This is lie, but it's anything but lying here. This is factually correct, that expectation of x is actually the expectation of x given a. Again, a mouthful, but that's how it means that. It says that you can compute an unconditional mean by averaging conditional means. So as you can see, expectation of x is obviously unconditional, but then it is given by averaging, because expectation is actually is an average. Again, we'll actually see that in a moment. Expectation of x is given by expectation of x given a. So as an example, we'll just look at this one. So expectation of y1 is actually probability d equals to 1. Okay, so that's the probability part. Again, so this is where the probability part comes in. So then that's multiplied by expectation of y given 1, y1 given d equals to 1 plus probability d equals to 0, expectation of y1 given d equals to 0, right? So that's the whole part here. We'll just see in a moment where it's coming from. So we have looked at the differences between ATE, ATT, and AU. I hope that's already clear. I'm not going into that one now, but you can actually also show that ATE is actually equals to probability of D equals to 1 into ATT plus probability D equals to 0 into ATU. Okay, so that's also derived from the earlier parts of the discussion that we had. So once again, if we go back to this particular equation here, so there's another formulation that we can look at, which is the ATE is equals to e to the power expectation of yi minus y0, which is expectation of yi minus y0 given D, right? So this is basically coming from the law of iterated expectations. Now if we just look at this part here, this is basically, we are going to expand this part using the definition of expectation. So, which is the case for, suppose, a discrete random variable. So expectation of expectation of yi minus y0 given D is actually expectation of fd. So if you look at this one here at the bottom as well, this will become even clearer. Expectation of fd is actually summation of f of d multiplied by probability of D equals to D. So if you look at this one here, what happens is this entire formulation on the left hand side, this expression becomes simply this part here. Okay, so this is happening because of this is following exactly from the definition of expectation. This might look a little confusing at first, but all that is happening is expectation of x given a is simply given by the summation of, again, this is for discrete random variable. Remember, for if it's continuous, it will just become integrals and you'll have to get that dx into that as well. So summation of I xi into probability of x minus x equals to xi given a. So that's pretty much, so you have the variable xi, the variable values, which obviously you are summing over for all values of I, and then you also have the probability. So that's pretty much so function of D here, that's basically your xi here, and that remaining part here in this general formulation becomes this rest of the part. Now what is this part on the right? This part here, probability of x equals to xi given a, this you can actually get from Bayes theorem. Okay, so that's where Bayes' theorem comes into picture, because this is conditional probability, and from there you can actually get this value, probability x intersection of a divided by probability of a, or rather probability of x equals to xi intersection a by probability of a. So that's the Bayes theorem which is coming into the picture here, and you can that formulation you can actually derive from the Bayes theorem's formula. So this is an example, a simpler example, just to explain what's going on here. So suppose x is a fair die roll. I mean, it's a fair die, so you have 6 rolls of it from 1 to 6, and obviously let a equals to x is even. So we are trying to understand the probability of an event a, that the outcome is even. So there are obviously 3 probabilities, right? So which are, so 2, 4 and 6. So therefore it's half out of, half of all the possible values, half of all the possible events. So therefore it's half, probability of a is half. Now possible values of x under a, 2, 4 and 6, right? That those are the only ones which are even, and each has a conditional probability of 1 by 3, right, if you think about it. So therefore expectation of x given a is nothing but 2 plus 4 plus 6 by 3. If you look at this formula here, if you just plug it in here, you know so that's what you pretty much get. 2 plus 4 plus 6 by 3 is equals to 4. So that's pretty much obviously the average of x given that x is even. Okay, so that's basically where it comes from. Like if you were to look at look at this formula as a sort of an average, this is, we talked about this before as well. If we just go back to this part here, so expectation of x given a is basically average of x given event a. This is why so this example actually explains why, because this is all coming from the concept of conditional probability. um taking cue from this particular expression here, we can actually see that if D has only discrete conditional probability. Remember, we are talking about discrete random variable, sorry, rather. So discrete random variable, we have 2 values of this discrete random variable, capital D, which is 0 and 1. So for 0 and 1, this expression simply becomes f of 0. If you go back here, um So this simply becomes the summation of these two cases, right, where f is equals to 0 and the other case is f equals to 1. If you just plug in those two, this is exactly what you get. So f of d here has been predefined here as, this part here in this example, and then if you plug that fd back into that equation, it simply get that, the summation of these two cases, uh, where d is 0 and in other case d is 1. So this was the whole explanation. I talked about the important part of expectation, the mathematical concepts of expectation, which are important to understand the different treatment effects. These are the most foundational definitions in causal inference theory, and I think if one can actually understand these well, then they can move on to the other advanced aspects of causal inference, like causal modeling and all. But yeah, I don't think there's any skipping this part. So that's why the statistical foundations are important. Hope this was useful. Of course, this is not nothing new to people who are already familiar with causal inference. For them, this will probably be just too much of a beginner refresher, if at all. But yeah, if you still have any thoughts or questions or any additions to make, please feel free to do so. For marketers, though, this can be actually a little heavyweight because you're not doing a lot of statistics all the time. But I definitely think that in the coming days, causal inference is going to become big. So do pay attention to this and try to increase knowledge in these areas as well. So thanks for watching. So long for this video, and I'll see you in the next one.